So what does this give us? This gives us what's known as the substitution rule for definite integrals. And that's basically stating that if I have some function, definite integral like this, if my g prime of x is continuous on AB, and if f is continuous on GB, then what we have is we can substitute. With a u. Notice how this is exactly what we did above, right? When I have g of x making equal to u, then I have g prime of x dx equal to du, then my dx is equal to du over g prime of x, which is how this g prime of x gets cancelled, right? G prime of x. Here, if I convert this to u, I get f of u, and then g prime of x here will be cancelled with the g prime of x that appears on the bottom. And so that's why we have this. And then these limits on the top, these are coming from this problem that we had just right before, where we converted the 4 to the 12 and the 2 to the 2 so that we make sure the area doesn't change. And so this is where this is coming from. And notice how this is just nothing more than the chain rule, right? A lot of these things that we're doing, implicit differentiation, substitution, everything is kind of coming from the chain rule. That's why in the beginning I emphasized the chain rule, because we really need to know how this is working. And so let's do another problem, because like I said, this is very confusing. And to remember, what we want is we always want there to be something there for us to be able to cancel. Here, if you notice, we don't really have something to cancel. This is confusing. What we can do is we have this ax, so let's get rid of this a, I guess, first. Let's see if that makes life easier. So let's do the thing and make this. So then du is equal to a dx, which implies dx is equal to du over a. And so we have cotan of ax dx. This is equal to cotan of u du over a. So I can bring out an a. Okay, that kind of made life easier, but I still have this u to deal with. Okay, well, let's figure something out. Let's see what we can do. I need something to cancel, right? I was just mentioning this before. I need to have something to cancel. So let's see what this cotan equals. Cotan of u, this is just cosine of u over sine of u, right? Oh, now we have something that we can potentially cancel, right? The derivative of sine of u is equal to cosine of u. And we have cosine of u on top. So this is literally kind of what we want. So let's do this. Let's substitute again. And remember, you can substitute multiple times. I don't think I've said this actually, so I can't say remember. You can substitute multiple times. Just like when we were doing L'Hopital's rule, you can use it multiple times. You can substitute multiple times. So let's substitute again. So since I have this, let me try this. Let me do... Actually, we have a little time. So I want to actually do something stupid. Because what I also kind of notice, right? Well, not stupid, it's actually smart, is that I have the same thing here. So let me actually first try this. Let me first substitute this and see what happens. Because here we have two options, right? And this is the point. Like, a lot of times this gets confusing. So let me go over something that doesn't work And then you can see what to do in that case. So let me try something that doesn't work. So I get t. So I get, here I take the differentials of both sides. This gives me minus sine of u du. I want to replace my du, so here I can have du is equal to dt over minus sine of u. And so here when I try to plug in cotan, so here I'll just replace this directly with cosine of u, sine of u du. So here when I plug in, I get t on top, right? Cosine of u becomes t, sine of u, and now my du becomes this. But here I multiply t dt minus sine squared u. I've now made my problem worse. Right? I still have a u and a t. The way around this is technically to remember that cosine squared u plus sine squared u is equal to 1. So cosine squared u minus 1 is equal to sine squared u. Yeah. And I think I talked about this a few times. So we'll do this notation, because I was mentioning that I like this better. I don't know why for squared we always put it there. It's stupid. Anyway, u. And so what do we have? I can replace this. So here I'll do this here. Is equal to 1 over a t dt over minus this. So we have cosine u squared minus 1. But here I know what cosine u is, right? This is t dt over t squared minus 1. This looks complicated, right? It looks like you might be able to do something, but this looks complicated. So let's actually try. Let's pretend this is not what we want, right? And let's try what happens when I take t, we'll do it here, is equal to, so this was not a good idea. So let's try the other one, sine of u. I don't want something more complicated. If it's more complicated, it's doing too much work. I don't want to work a lot. So let's try t is equal to sine of u. dt is cosine of u du. So du is dt divided by cosine of u. And so here what we have that the integral, right? So let me rewrite this out. The integral of cosine of u over sine of u du. So here we have 1 over a. Cosine of u stays. I haven't touched this time. Sine of u in this case does become t. And du becomes dt over cosine of u. So this replaces this, and this replaces that. Okay, and this time cosine of u and cosine of u cancel, so we get 1 over a dt over t. This is so much easier. That we know. So let's plug these in. What does t equal? Well, t, remember, is just sine of u. And what does u equal? Because we're not done, right? We want it in terms of x. U was ax. ax. And then we remember our plus c's. And we get our solution. So this is kind of how we do it. Now remember, when we want to do a definite integral, we would have to change the parameters. So if I were to do 0 to 1 here, for example, right, I would now have to keep track of these. Or I can plug it in. So I can either keep track, 0, 1. I don't actually know if these are good decent numbers. Actually, I know they're not decent numbers. right? So in this case, if I were to do this, then I would not have this anymore, and I would have x equals 0, x equals 1, all the way to x 0, 1. Yeah? So if we're doing the definite integral method, you would do it this way, or you can plug in right away and change this. So here we can make u is equal to ax. So if x is equal to 1, this top part becomes a, this bottom part becomes 0. Okay, so then now when I substitute, so in this case, I can do a. So here I'm going through all of the options. Maybe I shouldn't have deleted, but whatever. And then here, when I do this, I do sine of 0. Sine of 0 is still 0, equals sine of 0. And then I don't know what sine of a is, so it's just going to stay here as sine of a. And then here, I can plug in right away. So notice how this is not going to work because we have this when I plug in thing, but whatever. Sine of a minus, we'll do it this way, natural log of 0, right? So this is kind of what you're thinking of doing. So we still have, we don't have too much time, but I still wanted to finish. I think there's only one page. So I do need to cover this as well. And so this should be very simple. It's, well, not simple, but it should be fairly quick. And it's basically trying to figure out the integrals, the definite integral of even and odd functions. And this is going to be our last topic for the year. So we actually ended up doing everything that we wanted for the year. So congratulations, we're almost done. So remember, what were our definitions for even and odd, right? Even is when we plug in a value, a minus value, we get the function itself. And odd is if the negative kind of pops out. So here we have some examples. And so you can kind of, let's see if you remember what each one was. So this one is even. This one is odd. This one is odd. And then what is this last one? It's neither. To be fair, it's not even a function. Not even a function. Not even a function. Actually, yeah. So it's so yeah. And so some things we note right off the bat is that if I have two even functions, so I want some properties. This should have been red. There we go. Bloop. Red. And so we're going to have f and f be even, and then g and g be odd. Okay? So if I take two things that are even and I multiply them together, then it should be even. If I take two odd things and I multiply them together, they should be even as well. Right? Because think of it this way. If f1 of minus x, f2 of minus x, this is just f1 of x, f2 of x. So no problems. And then for g1 and g2, these minuses come out. g1 of x. But then since we have two minuses, they cancel. And so it doesn't change. And so we have even functions. Similarly, if we multiply an even and an odd, we'll get an odd function. That's kind of weird because this is different than how we do normal things, right? 3 times 3 are two odd numbers, and that gives us 9, which is an odd number. So this doesn't work the way we normally would consider even and odd. So just note that. These are not how we normally consider things. But there's a very nice property that comes with integrating even and odd, finding the definite integral of even and odd functions. if we have an even function, then we don't have to take the entire integral. We can just take half and multiply by 2. And this you can very clearly see for this even function on top, right? If I take something and I go from this point to this point, right, and I want this whole area, well, it's the same on both sides. So really, I can just grab from 0 and do 2 times this side, and it's the same thing. So we have that. For odd functions, taking it from minus a to a is actually just going to give us 0. And let's consider why. So here, if I have this part to this part, here we have positive area, here we have negative area, because it's below, so it's negative numbers, right? So it's kind of weird when you consider it this way, but this we can think of as negative area. And so these are going to cancel. And so similarly here, this part and this part are going to cancel. And so we're just going to end up getting 0. So sometimes if you see some big, long, complicated formula, and then you notice that it's from a to minus a, then the best thing to do is quickly see, well, what is this, even or odd? So let's plug it in. Let's see if it's even or odd. Minus x squared sine of minus x minus x to the 7 plus minus x cosine of minus x. This is an even function. This is an odd function. This is odd. Actually, we can do it that way. That's easier. Bam. So let me delete this. This is even. This is odd. Even, odd. This is odd. This is odd. And this is even. So even times odd, right? This gives us, from number 2, odd. Same here, odd times even is odd. And when we're adding things, we're going to keep them the same, right? So if I do f of x plus g of x, it doesn't matter if they're all the same. Either we can take out a minus, so if these are the same, g1, g2, I can bring out a minus for both, which means I can pull out a minus in front. Right? So here, this basically gives me an odd function, which basically means I can use property 4. So by 4, this is just equal to 0. So instead of trying to calculate this big, long antiderivative, we could just solve this and we'll be done. Or we can just notice how this is even and odd and notice that, okay, that's going to be 0. That's it. And so that's it. This is the last, so next lecture will be practice. And so I assume some people are not going to watch this. So I'd like to say thank you for being in my class. I know this class has been turbulent. I know there's been times where, here's a little flower. I know at times there's been times like when exams came around, it's been stressful. With the whole coronavirus thing, it's been stressful. Online teaching has been stressful. I know we've all been stressed. I know exams have been harder sometimes than we thought. I know things have not always gone accordingly to plan. But I hope you learned a lot from my class. It was super enjoyable having all of you. Keep learning, keep growing. And sometimes the hardest problems are going to teach us the most. So just because a problem is hard or complicated, sometimes that's going to be the best challenge. It's going to teach you how to go further in life. So yeah, thanks again for being in my class. I love you all. Have a phenomenal life. And if you're here on Friday for lecture, then I'll talk to you on Friday. If not, ciao.